So a while ago, I made a video about the AS5600 and hacking the I2C protocol with this particular chip by hand. And I was able to do this by bit banging it with buttons. And as you could see here from the previous video, I basically did used a separate data line and SCL line, or the clock line, and basically using the I2C protocol, I was able to do this by hand. And as you could see in that video, the timing wasn't so precise in terms of speed, so I could just do this manually by hand. And at that time, the way we did this was we basically wrote to the address of the I2C device, and then we wrote to a specific address, which is the raw angle sensor of this magnetic rotary encoder, in order to get the 12-bit digital output out of it. And then we're able to get data, as you can see here, data coming through on the data line. And then this is what it looked like on the oscilloscope with the three addresses, and there was a sequence involved in order to initialize the chip so that we can get the data out. And here's the data coming through. And in a previous separate video, I made a receiver circuit without using a microcontroller that would receive data from the device. And here's the timing diagram of the receiver circuit that was required, basically 8 clock ticks per data. Today I'm going to focus on the transmittal, or the initialization circuit, which requires writing to the chip, then writing to a specific address on the chip, and then reading from that data. And so the way I'm going to implement this is by using no microcontroller, but just a circuit using counters and transistors and shift registers. So the way to do this is by taking 2 separate lines and adding the signals that you need on all of those lines, and then putting them through a big giant OR gate using diodes. And I'm going to do this step by step for both the SCL line and the SDA line, which is the data line, and ultimately outputting them into the I2C device, which is the AS5600 magnetic rotary encoder, to get the angle data out. So we're going to start the process by first starting with the start condition, then writing to the specific address, and repeat starting, and then putting in a read signal. To implement this, I'm going to be using 2 chips here. The one on the right here is a Schmidt trigger inverter. There's 6 of them on this, and this is going to create our clock circuit, basically a low frequency oscillator. And I have a large resistor and a relatively large capacitor, 10 microfarad capacitor, and 300, I think it's a 300K resistor, and basically going from input to output. And the output of that is going to be going to the clock circuit of a CD4017 decade counter. And what this does is it just counts to 10. I have it set up to be counting to 8, and then or to 7, and then resetting. So it's just going to have 8 counting from 0 to 7, and then resetting over and over and over again. And so we're going to use this to recreate our start condition on the I2C protocol. So let's make it happen. So here we have the output of the low frequency oscillator oscillating slowly, and that's using the large resistor and capacitor combination. And now, when I go to the decade counter, you can see it counting here. I have the LED lights just to show the outputs, going from 0 on the left to 7 on the right. So now, let's recreate the start condition for the I2C protocol from the first two outputs. So now what I did was I took a diode from output 0 and output 1, and I put two diodes going from output 0 to this line, which is going to be the clock line, the SCL line of the I2C, and output 0 also going to the data line. And so in this way, these two diodes function as an OR gate. So when the output is 0 or 1, the SCL line stays high, and there's no break in between, and the output 0 stays high only for the first part of the data line to recreate the start condition. So let us see. So now I have this counting. The yellow line is the oscilloscope probe on the left here, this one, and the diodes from outputs Q0 and Q1 are going to that through two separate diodes to the same input, and the output of pin 0, or the output Q0, is going to the data line of the I2C. So in this way, we're gonna, every time it goes between 0 and 1, it's going to recreate the start condition. So let's watch it. And that's the start condition. Works beautifully. So on to the next step. I've taken out the LED lights now, so this whole process can be seen more clearly. But when I switch on the circuit here, you'll see the start condition come up as it resets to 0 right away. Without the LED lights taking away some of the voltage, it actually goes to 5, and that's the start condition. And it just repeats because it resets to 0 every time. So now we're going to attempt to clock in some data. So now I have a new setup where it's the same as before with the diodes, but I have, in addition to this, the output from pins 0 and 1 going to the SCL circuit, I'm also having them go to a transistor-based AND gate, the base of a transistor-based AND gate, so that during the first two parts of the sequence, which is the start condition on the SCL line, I have this turning this transistor on with a 100K resistor. Then I have the main clock signal through this other yellow wire right here going to the collector of the transistor. The emitter of the transistor with a pull-down resistor there, a large pull-down resistor to ground, ultimately ends up being the clocking signal, and it's going into the clock through another diode, because I plan on manipulating the starting and stopping of the clocking through different diodes at a later point. And so when I do this and I start the circuit, I'm going to turn it on now. You get the start condition, and that's it. And then the clock should be stopped at this point. When I test to see what's going on with the CD4 107 or 4017. If I go to the second input, Q2, and I put an LED there, it should be stopped at Q2. See, it's not counting. I just put the LED into Q2 output. So basically it's stopped at Q2. So now we needed to clock in to the next part of the sequence, and so we're going to make that happen with a separate oscillator here. So now I have this second setup here. It's a second oscillator using a 22K resistor and a 47K capacitor, and it's a little bit faster than the original oscillator, and you can see it there. So the clock is still stopped at Q2, and now we're going to activate the second oscillator using a similar mechanism. Now it's getting a little bit more complicated here. What I did was I wanted two things. I wanted the SCL output not to be tied to the same output as the second oscillator. So basically I took the outputs from Q1, Q0, and Q2 from before the diodes, and I put them through 3 separate diodes going into that AND gate, so that the main low frequency oscillator does the start condition at Q0 and Q1, and then takes a break, pauses at Q2, but goes through Q2, and then advances to Q3, and then the clock stops. And at Q3 is where I have an LED light here, and so when I turn the circuit on, it should do the start condition, pause at Q2, and then light up the LED at Q3 and stay there, as the clock should be stopped. So let's test it out. And let me turn this on and see. There's the start condition. The blue line is the second oscillator. And that's it. It goes to Q3 and stops. So now we can start the second oscillator and put that into the clock line at this point. So now I've taken the output of Q3, and what I've done with it is put it through a 100K resistor to the base of this transistor. Now the second oscillator, the faster one, I have going through this blue wire through a 47K resistor into the collector of the second transistor. And what I'm going to do is, now I have the blue oscilloscope probe measuring the output from the emitter of this transistor. So when I start the circuit, you should see the yellow line, the yellow curve is still on the SCL line, and the blue curve is now on the oscillator. So now, when I turn it on, you should see the start condition on the SCL line, and then the blue, after that's done, and after a pause at Q2, it should put the oscillator on. So there's the start condition on the SCL line, and then it goes down, and there's the blue oscillator line oscillating quickly. So now we just have to OR those two signals together with another diode. So let's see how that looks. So now I've put the output from that transistor through this long black wire here, this one, down to another diode going into what our SCL line is going to be, and that's being read by the yellow wire here on the oscilloscope probe, the yellow tracing, and I put the blue tracing back on the SDA line, what's going to be our SDA line, and let's see what those two signals look like together when I turn on the circuit. So when I switch it on, what you should see is a start condition followed by a pause, and then you're going to see the other oscillator go on to clock in the sequence for the data. So let's see it. Start condition, and there goes the oscillator, the faster oscillator. Okay, the signal is building, and it gets complicated as it goes on, but let's keep going. Now we need to put some data on the SDA line. So for that, we are going to use something that loads parallel and gives out serial data. So we're going to use a shift register. Let's see how that works. So now I've added to this circuit to get some data 74HC165, which is a parallel load serial output shift register. And the way this chip works is you have the power and ground on pin 16 and pin 8, and then you have inputs A, B, C, D, E, F, G, H, and so the output is H first in serial, and the output comes from pin 9. And so I have here preloaded the sequence, the first sequence which we need, which is to write to the I2C chip address that we want. This is there's a leading 0, then there's a 0, 1, 1, 0, 1, 1, 0, 0, and that's the serial input. So let's see it in action. The way I have this hooked up right now is that this is the white wire. Here's the clock inhibit pin, and that has to stay low. And the clock is coming right from that second oscillator, where it's going to be the faster oscillator. And this pin 1, is the I have it set up with a capacitor and a 100K resistor to ground, and what that does is it loads it on startup and then pulls it high. The output at the moment I have from pin 9 going through this resistor to this LED, so we should see when the oscillator starts going the output of 0, 1, 1, 0, 1, 1, 0, 0. So let's see it in action. Let me turn it on, and we'll see the oscilloscope screen too. There's the start condition. 0, 1, 1, 0, 1, 1, 0, 0. Okay, now let's put that into the SDA line with another diode to OR it in there. So now I have the output of the shift register going through another diode into the SDA line. So let's start it up and see how it looks all together for the start condition and the first sequence. Here goes. Start condition. Pause. And there's the data coming through on the SDA line. 0, 1, 1, 0, and it ran out of data. So now we have to get it to stop after 9 pulses, because you need the acknowledge bit too. So that begs for another counter. Now, since we're creating this big for loop here, to clock in the data for the sequence, we need a total of 9 pulses, 8 for the data, and the last pulse should be the acknowledge bit. And so in order to do this, I've set up yet another CD4017 decade counter, and what I have is I have it counting to 9 and then resetting. So now in order to test this, I'm going to show on the oscilloscope how the signal looks. So you have here on the blue tracing is the clock, and on the yellow tracing is that 9th pin. So you can see every 9 clock cycles on the fast oscillator, you have a pulse on that. And so just to count it, 1, 2, 3, 4, 5, 6, 7, 8, and on the 9th one, it goes up. And then I have it set with this little yellow wire here to reset. And what we're going to do is we're going to bring that signal over to our original CD4017 counter through a separate diode to advance to the next step of the sequence. So let's do that. So now here's the final product, and you'll see it cycling through in a second. It counts to 9 and then resets. So let's do that. Here we go. Start condition. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's going to go one more time. Start. Here's the data at the bottom. First clock pulse. And there's 8 total clock pulses with the data, and then an acknowledge pulse. So now, there we have it, the first part of the sequence built in with the start condition and writing to the address of the I2C chip. For the last part of this, I've taken the original signal, and since it has to be delayed a little bit, the clock signal after the data, the SCL after the data, I've put it through a low-pass filter with a 2K resistor and a 22 nanofarad capacitor going to ground with a 100K resistor parallel to it. And what that does is it delays the signal, and it goes through an op amp as a gate to trigger converter, basically a comparator. And so what you get is a delay in the signal. As you can see here, the rise in the signal, the yellow line, the yellow tracing is the original signal, and this is the delayed signal. And so what I'm going to have is going to the SCL line, the final product is the blue tracing, because that's going to go after the data, and it's delayed by just a little bit. To see the actual delay, let's see, let's make it higher resolution. So you can see the delay here is about 10 microseconds, which is an infinite amount of time. So let's see what it looks like on the falling edge. Very good. Okay. Start condition. Here's the clocking. 2, 3, 4, 5, 6, 8, 9. Okay. Start condition. There's the data and the SDA. Now, let's look at it with a delay on the signal. I'll change it to normal mode, and there we go. And there's the delay, 400 microsecond delay. Since each clock pulse must fit within the entire data cycle, you can see the data line going up and down and the clock pulse lower edge ending before the clock signal goes down. Now, to build this out further, all we need to do is just add a second CD4017 counter to cascade it, and a second 74HC165 preloaded with the second part of the sequence, which is the 00001100, which is the raw angle sensor of the AS5600. And here's what it looks like. After that, you need a repeat start condition, which you can see right here. And I have that made in the exact same fashion that I made the original start condition on the following sequential outputs of this original master CD4017 counter. So here's what it all looks like in better resolution. Start condition, followed by writing to the address of the I2C, an acknowledge bit, and then writing to the raw angle sensor, and then acknowledge, and then a repeat start. And then all we have to do to finish it off is in the following Q7 output, we have to add just one more shift register and one more CD4017 counter to clock in the remainder of the sequence. After that, the I2C device should be ready and able to transmit data, and then we'll have Q8 stop the clock and activate the receiver portion of it, which is going to be a much faster oscillator to receive data on the fly quickly. And in the interest of time in this video, since it's already getting long, I'm not going to show all that, since it's just a repeat of what I did at the beginning to essentially code this in hardware. In this way, the master counter forms the main loop of the program, and all the other parts are just functions that are clocked in using various timers and OR gates to add all the signals together in one or two lines in this case. So now I have part one of the initialization sequence for an I2C line, and basically this addresses the first byte and sends the first sequence and does a repeat start after initial start condition. So it took a little while to get it to work, but here it is. Let's see how it works when I turn it on. Let me put it back to 5 seconds. Here it goes. Start condition. Now the clock should start. 1, 2, 3, 4, 7, 8, 9. You see the data line in blue and the SCL line in yellow. There it goes. Repeat start after 18. And now we need to put in the rest of the sequence, the read from part, and then we can implement the data part, the data receiver part. So here's what the final product looks like, and an explanation of all the data. And I'm going to leave you guys with the schematic as always. Thank you for watching.